Hello, class. Welcome to our next examples on section 4.6, dealing with the counting principles. Let's go ahead and go through our examples for today. Again, we're just trying to get some more versions of questions dealing with the counting principles, such as permutations and combinations, and then the identical pieces dealing with repetition of letters. This question is what we ended with the other day, but we're just asking a different question of figuring out the probability of at least 2 women on the board as part of the committee. So there's two different ways that you could do this. One is you could figure out the probability of having 2, then 3, then 4, then 5 women on the board. Or you could do the complement. So I chose to do the complement idea in this situation, which would be find the probability of no women on the board or the probability of 1 woman on the board, and then get rid of that out of the group. So for this question, I basically took the 7 men and said all 5 had to be on, and then of the 6 women, none. Divided by 13, choose 5, because there's 13 total people, choose 5. And then same thing for 1, and that'd be 7, choose 4, and 6, choose 1, and then divided by 13, choose 5. I subtract that out from the group, and I get 0.821. So it should be fairly likely that at least 2 women are in the group then of that 5-person committee. One other thing that what may happen here is they may just say how many ways can you have at least 2 women. We didn't talk about that with the one from the other day. But if the question is how many ways could you have at least 2 women on the board or on the committee, you'd have to find the probability, or you'd have to use the numerators. So you'd have to use this idea with the 7 and 5 and the 6 and 0 with the combination. But you'd have to do it 2 women on the board, 3 women on the board, 4 women on the board, 5 women on the board or the committee, and add up all of those options. So there's a difference between the probability questions and the how many questions. So you want to think about that as you're looking at those scenarios. The next question deals with the lottery. So the first one we're going to look at is the Mega Millions, which is just pick 5 numbers from the numbers 1 to 52, doesn't matter the order, and find the probability that you win. Now, they're going to probably have these as fraction answers, so you're just going to have to find what 52 choose 5 is. So you can write that in a couple different ways, but 52 choose 5 is this 2,500,000 number. Honestly, the most common mistake is you type a number in wrong from the answer because those numbers get very large very quickly. But the ways you win is just 1, so it's 1 out of that number, and that would be your final solution for that situation. The problem with something like the Mega Millions is there's less than 3 million ways. So if there was a $5 million jackpot, if you had enough money to buy all the tickets, you could just buy all of them and then win anyway. So what's been adjusted here is the Mega Millions is now from 1 to 75. Okay, so you pick those, and then there's a special number. Okay, it's sometimes called the Powerball, for example. Okay, where you select one number from 1 to 26. So the probability you win now is you got to pick 5 of the 75. So that's 75 numbers, choose 5 as a combination. And then 26 choose 1, also the combination. Multiply those 2 numbers together, and all of a sudden, I'm almost to 500 million. Okay, so the difference here is you had 75 choose 5, and then 26 choose 1, and you combine that all together, and you get 1 out of that total 448 million number. And then the idea here would be that the winning amount is always less than this, and unless it gets to one of those really high numbers. But still, your likelihood of winning has gone way down. And so if you had a bunch of money investing it and buying lotto tickets, probably isn't the best option then. Next question deals with drawing 5 cards without replacement from a standard deck. So the important thing is when you draw the 5, it doesn't matter the order in which you draw them. You just get 5 cards without replacement. So the easiest way to find the probability of at least 1 ace is to do 1 minus the probability you had no aces. So we're going to find the probability you have no aces. So there's 4 aces in the deck, and I want 0 of them. There's 48 other cards in the deck. I want 5 of them. And then again, notice that 4 and 48 become 52. 0 and 5 become 5. I find that number using the combination buttons on my calculator. 1 minus that would be just over 34% or 0.341. Remember, for most questions, for decimals, you're going to go to 3 significant digits, so zeros and then 3 numbers after that. And that would be the probability of having at least 1 ace in your hand. The next one says 4 of a kind. So what we're going to pretend is, let's just say it's 4 aces. So that's 4 choose 4 because there's 4 aces that are in the deck, and you want all 4 of them. But then don't forget you need a 5th card, so that would be 48 choose 1. And then 52 choose 5 for the denominator. This fraction right here with the combination, that's only for one type of card. The issue with the deck of cards is there's 13 types, ace, 2, all the way to 10, jack, queen, king. So once you find this answer, you're going to have to multiply by 13 because there's 13 different ways to find that. Notice in my answer as well that there are all these zeros and then 3 significant digits at the end. Okay, the next thing is a royal flush. The royal flush is kind of easier to figure out because there's just 4 of them. There's one for each suit because you have to have 10, jack, queen, king of all of the same suit. So there's just 4 options for the numerator. The denominator should be 52, choose 5. And this probability probably explains why, if I've played cards even my whole life, maybe I've only gotten this hand one time in my whole life. So when you're looking at this, this should be very unlikely. So if someone keeps saying, well, yeah, I keep getting that every evening, you say, well, something's up with how you're dealing, or something's going on here. Because notice the difference. Just to have at least an ace was 34%. Having 4 of a kind was really small, but this is astronomically smaller. Which makes sense because there's only 4 options out of all of the different types of 5-card hands that you could have in a standard 52 deck. Next question we're going to look at deals with Social Security. So Social Security first is 3 numbers, then a dash, then 2 numbers, then a dash, then 4 numbers. So in all, there's 9 numbers for Social Security. So let's just say you want the probability that you guess my Social Security card or number correctly. There's 10 digits for each spot, so 10 times 10, 9 times, so that would be 10 to the 9th. Not 10 times 9, 10 to the 9th power. And so if you want to guess correctly, there's only one way you guess correctly out of 1 billion ways. This is probably why if someone has your Social Security number, it wasn't guessed, it was found somehow on a document or figured out and hacked in some way on a site, because the chances are so unlikely that they guess your number correctly. Now, something interesting about Social Security is there's not that many numbers actually available. Social Security numbers, according to the government at this point, cannot start with 3 zeros, and cannot start with 3 sixes, and cannot start with the number 9. So you can't have 900 to 999 on your 3 starting numbers. So let's go through a little bit about Social Security. Not to go into too much detail, Social Security originally was set up that the first 3 numbers are from where you're from. So they were put out in that way so that the first 3 numbers would kind of be like an area code, like a phone number. That idea was really helpful when people didn't move around as much. Now it's kind of hard. With people moving all the time, Social Security numbers become a little bit more challenging to keep track of. But if you think about it from the perspective of this is my 3 numbers are where I'm from, no one would want to have 3 zeros because that would say you're from nowhere. So they took that out of the equation. As a parent, I might be a little suspicious if my child had a Social Security number where it says where they're from starts with 666, and if you're not sure what that means, I'm sure someone would be able to inform you. And then this 900 to 999 is essentially just a reserve. Okay, it's like they left those numbers out in case they need them later. Up to this point, we haven't needed them. If they were needed, then they would start flooding them in with the 9, starting with the 9. If we end up with too many Social Security numbers, we would just say, okay, well, let's add a digit to the end. But you have to get rid of these. So let's start with 000. So 000 means there's only one option. We're trying to figure out how many options start with 000. There's one option for the 3 zeros, and then it's 10, 10, 10, etc., 10 to the 6th. The same exact thing would be true with starting with 3 sixes. So there's a 10 to the 6th and another 10 to the 6th. And then the 900 to 999 is 10 to the 8th because all that's required there is that the first digit is a 9. And then it's 10 to the 8th power. From there, you subtract those out, you get rid of some of the numbers, and you end up with 898 million Social Security numbers. At this point, the population of the U.S. is less than that, so it's not an issue at this point. Once people would have passed away, they could start reusing numbers eventually as well. But if they needed to, they'd use the reserve, and then they could also add in a digit in order to find some more options for Social Security numbers. That's all we have for today. We're going to be looking at some review questions in terms of some of these things over the next couple days. Also, you don't want to forget about dealing with the questions like the chart, where you have to figure out the or statements or the and statements. Those are also going to show up again as we move forward. Have a good day, everyone.